Now, this post got a lot of attention on Facebook, and in spite of the junior high graphics, you might even understand why.
Something terrifying just broke open beneath Yellowstone. A sudden crack, 100 feet long, tore through one of the world's most closely watched volcanoes. Satellite alerts, emergency calls, and ground crews all zeroed in on what could be the start of something much bigger. Steam rising, gas venting. The land itself is shifting. This isn't science fiction, it is unfolding in real time.
It's one of the largest supervolcanoes in the country, and recent work out of the University of New Mexico led to a breakthrough discovery that could help geoscientists better predict an eruption and save lives.
What caused this rupture? Could it be the first domino in a long-feared chain of events? Join us as we look into the 100-feet crack on Yellowstone and what scientists are saying about it. The massive 100-feet crack at Yellowstone. On June 22, 2025, satellite geodesy platforms orbiting above the western United States detected a sudden, elongated surface anomaly in Yellowstone National Park's northeastern sector. Ground teams mobilized within hours, and what they found was alarming. A jagged crack slicing through an active geothermal field east of Norris Geyser Basin. Measurements taken on site by Yellowstone Volcano Observatory, geologists confirmed that the fissure extended roughly 100 feet in linear distance. The crack's width varied from 2 to 8 feet across, with the deepest visible points descending over 15 feet. What more details do we need to know about this crack? Should the world prepare for cracks even more sinister? Brace yourself. What you're about to hear will blow your mind. The rupture cut directly through hydrothermally softened terrain, exposing underlying soil layers and fractured volcanic bedrock. Infrared readings recorded shortly after sunrise revealed thermal hotspots inside the chasm, with temperatures up to 90 degrees Celsius near the base. The split bore the hallmarks of brittle faulting behavior, characterized by vertical displacement and rapid structural failure. Satellite imagery later confirmed the fissure's precise location at approximately 44.798 degree north latitude and 110.676 degree west longitude, sitting squarely above a known caldera boundary fault. The first human to witness the rupture was Park Ranger Leah Forrest, who encountered the feature during a late-night patrol. At precisely 10:18 p.m., Forrest radioed dispatch described a roaring sound, followed by the ground giving way into a wide trench. Emergency responders and geotechnical staff were deployed overnight. Aerial surveillance conducted at dawn using LiDAR scanners from a low-altitude helicopter documented not only the crack's extent, but also minor landform warping in a 50-meter radius. These distortions suggested underlying tectonic flexure rather than shallow surface collapse. High-sensitivity GPS stations in the area, part of the Plate Boundary Observatory network, recorded eastward displacement of up to 16 millimeters over a 48-hour period with negligible motion to the west. This lateral shear, consistent with right lateral strike-slip motion, matched long-term fault activity mapped around Yellowstone's ring fractures. Importantly, a borehole tilt gauge located 300 meters southeast of the crack registered a sudden 0.7 degree shift, indicating subtle rotation of the ground mass beneath the fissure. Scientists immediately labeled the event a tectonic fissure due to its abrupt appearance and structural context. Unlike the slow subsidence typically associated with geothermal sinkholes, the crack emerged within hours and displayed clean wall separation, an indication of brittle deformation in stressed rock. By June 23, USGS volcanologists had installed field equipment to monitor stress transfer, edge creep, and any further fracturing. Extensometers anchored to rebar across the crack registered ongoing horizontal dilation at a rate of 2.3 millimeters per hour in the warmest zones. Simultaneously, airborne FLIR, forward-looking infrared, sensors revealed a linear plume of escaping steam and CO2 rising from fissure vents. Thermal cameras detected upwelling geothermal gas mixtures, suggesting the fissure had cut into shallow hydrothermal conduits beneath the surface. The crack's behavior, location, and associated thermal features elevated it to a Level 2 geothermal disturbance under Park Service criteria, triggering visitor access restrictions and localized evacuations. The impact on park operations was immediate. 3 major hiking trails were closed indefinitely, and the popular Norris Canyon Road corridor was restricted to ranger-led convoys. Tour operators shifted activity away from the affected zone, while local businesses reported cancellations from travelers concerned about seismic safety. Lodges in the West Yellowstone Township experienced a 22% drop in reservations within 48 hours, according to the Montana Chamber of Ecotourism. Meanwhile, drone photography of the fissure circulated widely online, fueling public speculation. In response, the Yellowstone Volcano Observatory issued a public bulletin emphasizing that the event was being closely monitored, but was not, at the time, considered a precursor to a volcanic eruption. Despite official reassurances, local emergency response units remained on standby, and the Federal Emergency Management Agency, FEMA, dispatched a geohazard assessment team to collaborate on contingency planning. Comparisons were quickly drawn to previous fissure events across the Yellowstone region. In August 2014, a 30-foot-long ground crack opened near the Grand View Trail, prompting temporary closures. That fissure, however, was shallow and inactive. In contrast, the 2025 rupture exhibited ongoing movement, a greater vertical drop, and clear signs of deeper geothermal interaction. Additionally, the Grand Teton National Park reported a surface split in 2009 following an earthquake swarm, but that crack was geologically separate, arising from shallow slope instability. What distinguishes the June 2025 fissure is its proximity to the northern rim of the Yellowstone caldera, a region defined by active ring fractures and known episodes of uplift and subsidence. Historical data show that similar ground ruptures have coincided with broader episodes of caldera breathing, where magma chamber pressurization causes periodic surface deformation.
We are due. Forget Yogi Bear. Okay, forget Old Faithful. It's sitting on top of a sleeping giant. It could destroy the United States as we know it.
Geophysical instruments placed along the fissure line revealed significant anomalies in the hours preceding its appearance. The University of Utah seismograph stations recorded a swarm of 16 micro-earthquakes between magnitude 1.8 and 2.5, all within a 3-kilometer radius of the rupture. Notably, a magnitude 2.3 tremor occurred at 3:12 a.m. on June 22nd, just hours before the crack was discovered. Spectral analysis of the seismic data indicated low-frequency harmonic tremor, a potential signature of fluid movement at depth. Meanwhile, surface deformation maps generated using INSAR, interferometric synthetic aperture radar, showed uplift of approximately 12 centimeters over a 200-meter band centered on the fissure site. These findings, combined with field tilt and creep data, suggested the crack formed in response to localized stress readjustment above a magma-heated zone. Further investigation revealed elevated concentrations of volcanic gases venting through the fissure. Portable multi-gas sensors recorded carbon dioxide levels peaking at 1,200 parts per million, nearly triple the regional average, along with measurable traces of sulfur dioxide and hydrogen sulfide. These emissions are typically associated with magmatic degassing and indicate a possible breach in the shallow gas seal that normally contains these volatile substances underground. Soil temperature probes recorded a spike of 16 degrees Celsius compared to baseline levels, with gas compositions resembling those found in fumarolic activity near Yellowstone Lake. The fissure essentially created a new escape route for subsurface gases, drawing attention to the interconnected nature of Yellowstone's geothermal and tectonic systems. To further assess the structural integrity of the surrounding land, geologists initiated a trenching project along the fissure's eastern edge. Preliminary trench logs described fragmented pumice layers, hydrothermally altered rhyolite, and signs of recent fluid migration. Radiocarbon sampling of organic matter embedded in the soil layers is underway to determine if the crack intersects with any older seismic scars. Engineers are also testing the potential for secondary collapse features, as overpressured steam pockets have been known to trigger ground failure weeks after an initial disturbance. Meanwhile, high-resolution photogrammetry and 3D laser scanning are being used to create a digital model of the fissure, allowing researchers to track microscopic shifts along its fault lines in real time. What more did the scientists discover, and what do they recommend? Let's dig deeper. What scientists are saying and the alarming possibilities. Just hours after the Yellowstone ground crack was discovered, scientists from the U.S. Geological Survey and the Yellowstone Volcano Observatory arrived at the scene. Their first job was to figure out whether the 100-foot fissure was caused by surface movement alone or if something deeper was happening underground. Early signs pointed to more than just surface damage. The crack appeared along a known fault zone in the northern rim of the caldera, and its sudden appearance raised red flags. Experts explained that such fractures often signal deeper pressure changes within the Earth's crust. The team quickly set up more monitoring equipment, including gas detectors, thermal cameras, and stress meters, to collect real-time data. Though they reassured the public there was no eruption in progress, the scientific tone behind the scenes was more cautious. A major structural shift, even without lava, can still hint at movement in the caldera's deeper systems, which are already under constant observation for any unusual activity. Geologists reviewed digital elevation maps to study changes in Yellowstone's crust. They found that the crack followed a northeast pattern that matched earlier fault lines. This zone is known for crustal extension, where sections of the ground slowly pull apart. In normal cases, this happens over years, but the sudden tearing seen in June was too fast for comfort. Yellowstone's surface lies above a massive chamber of hot rock, and even minor movement in these upper layers could affect pressure balance below. Rock types in this part of the park include volcanic ash and porous lava, both of which weaken easily when heated or soaked. When stress builds up faster than the rock can stretch, it eventually breaks. The result is what happened here, a loud, fast-moving crack in an already sensitive area. What puzzled scientists was the speed and size of the rupture, which seemed to outpace the usual warning signs. One possibility under discussion was hydrothermal explosion risk. Yellowstone has had violent steam blasts in the past, triggered by boiling water trapped beneath sealed rock layers. When pressure builds and the seal breaks, the release can be explosive. Though the June crack did not result in such an event, several scientists suspected it could have opened pathways for future steam pressure to collect. The gas readings around the fissure supported this theory. Instruments picked up elevated levels of carbon dioxide and hydrogen sulfide, both common in Yellowstone's geysers, but now emerging from an unusual location.
Here's the footage released by the USGS. It shows the eruption blasting out of a thermal pool, sending water several feet into the air.
Surface temperatures around the crack were also rising faster than expected. These changes suggested that hot fluids had begun moving into new areas, changing the underground plumbing. When that happens, it can shift geyser behavior, open new vents, or destabilize older ones. Seismic teams then reviewed the weeks leading up to the event. They found over 180 small quakes had occurred across the northern part of the park. Most were minor, under magnitude 2, but their clustering stood out. A few stronger tremors near magnitude 2.5 were recorded just days before the fissure appeared. The timing and location lined up almost exactly. Depth readings placed the earthquakes between 3 to 6 kilometers beneath the surface, below the hydrothermal system, but above the main magma body. This is a sensitive layer where fluids, gas, and rock all interact. One theory is that small earthquakes reduced friction along a fault line, allowing the crack to open. Another idea is that those quakes were caused by fluid movement, which then pushed the surface apart. Either way, it became clear that the crack was part of a wider set of changes, not just an isolated tear in the earth. Satellite tools also helped track recent ground movement. Using radar images, scientists measured uplift of nearly 12 centimeters in the weeks before the event. This upward push is often linked to underground pressure from magma or gas. GPS devices placed across the park confirmed the findings, showing slow but steady surface inflation. The key concern was not the total size of the uplift, but how fast it had accelerated in the days before the crack opened. This kind of change can indicate that magma or pressurized gas is forcing its way upward. In Yellowstone, even small increases in pressure can lead to big reactions due to the weak surface rock. Researchers began running new models to understand what these movements could mean over time. They stressed that inflation does not guarantee an eruption, but it is a common early sign of unrest. To prepare for possible worst-case outcomes, simulation labs began testing eruption scenarios. These models used real-time data from Yellowstone and estimated how different pressures and fractures could lead to larger events. One key model focused on the ring faults that surround the caldera. It showed how a deep crack could allow gas or magma to rise, changing the chemistry and temperature of surface features. The most extreme version of the model showed how small surface breaks, if they spread fast enough, could weaken the entire crust above the magma chamber. While this was not likely, it helped researchers understand the limits of the current system. Probability models suggested less than 1% chance of a large eruption in the next year. However, short-term risk was raised slightly, with a projected chance of 0.3% over the next 3 months. These figures are still low, but no longer at background levels. The final challenge was how to explain this to the public. Scientists held a press event with the National Park Service and emergency officials. They shared the data clearly and warned people to stay out of restricted areas. Officials stressed that the crack was being studied closely and that no explosive activity was expected at that time. The goal was to avoid panic while keeping people informed. Updates were sent out through mobile alerts, park notices, and official websites. Visitors were told about trail closures and reminded to report any unusual smells, sights, or sounds. Scientists avoided dramatic language, but admitted that the crack revealed growing instability in Yellowstone's upper crust. One researcher noted that every new fracture helps the team understand how the caldera is evolving. And with a system as large and complex as Yellowstone, even the smallest change matters. Now the question is there a pattern of eruptions at Yellowstone? Curious, right? You're at the edge of your seat, and it's about to get even better. Yellowstone eruption history and global implications. Yellowstone has erupted 3 times in the past: 2.1 million, 1.3 million, and 640,000 years ago. Each eruption blasted out huge amounts of ash and lava, changing the land and spreading debris across North America. The largest, 2.1 million years ago, released over 5,900 cubic kilometers of material. The most recently formed the massive Yellowstone caldera.
It tells us that there is activity in this supervolcano, which erupts roughly every 600 million years. And the last eruption was 640 million years ago.
These explosions followed long, quiet periods, then suddenly released intense pressure from deep underground. Could it happen again? Is another blast building up beneath our feet? Stay tuned. The most interesting part is still ahead. Geologists studying the ashfall layers from the last eruption found evidence of climate-altering effects that extended far beyond North America. Sulfur aerosols from the blast likely entered the upper atmosphere, reflecting sunlight and triggering global cooling. These atmospheric shifts may have caused short-term ecological disruption, reducing temperatures by several degrees worldwide. In North America, ash from the eruption was discovered as far east as the Mississippi River and as far south as the Gulf of Mexico. These ashfall blankets were meters thick in some places, enough to bury forests and disrupt photosynthesis. While no mass extinction is directly tied to Yellowstone's past eruptions, there is growing interest in how such events may have pushed ecosystems to the edge, particularly during periods of already changing climate. Studies comparing Yellowstone ash with other supervolcano deposits, such as Toba in Indonesia, highlight similarities in chemical makeup and cooling effects. To track Yellowstone's present-day behavior, scientists rely on a network of advanced monitoring systems. Dozens of GPS receivers are positioned across the park to measure surface uplift or subsidence down to millimeter accuracy. These devices record subtle changes in the landscape, often indicating underground movement of magma or hydrothermal fluids. Seismographs, maintained by the University of Utah and USGS, detect thousands of earthquakes per year in the Yellowstone region. While most are too small to feel, patterns in their location, depth, and frequency provide clues about subsurface activity. Infrared satellite imaging also plays a key role. These instruments can spot heat signatures from hot springs, fumaroles, and even unexpected steam vents, offering real-time data on thermal changes. Combined, these tools give scientists a layered view of Yellowstone's dynamic systems, from crustal tension to the distribution of hot fluids near the surface. Preparedness plans for a Yellowstone eruption exist at multiple levels of government. The Federal Emergency Management Agency, the Department of Homeland Security, and the Centers for Disease Control and Prevention have all contributed to simulation-based response models. These models account for different eruption sizes, from local hydrothermal blasts to continent-wide ash dispersal. Emergency scenarios consider everything from forced evacuations of nearby states to the national rerouting of food, medical supplies, and transportation. Ashfall, even from a moderate eruption, could paralyze air traffic across North America and contaminate water supplies in dozens of states. Long-term inhalation risks would strain healthcare systems, while power grid failures and crop damage would disrupt economic infrastructure. These concerns are not speculative, but built into federal continuity of government strategies. Reports from FEMA note that even a 1-inch layer of volcanic ash on city streets could block drainage, disable engines, and damage electronics on a massive scale. The global effects of a Yellowstone eruption would depend on the scale and duration of the event. In a large eruption, sulfur gases could reach the stratosphere and remain suspended for months. This would scatter sunlight, leading to a temporary drop in global temperatures, possibly by 2 to 3 degrees Celsius. Such a cooling period could delay crop cycles and lead to food shortages, especially in regions already facing instability. On a trade level, supply chains dependent on North American agriculture or air freight could suffer severe setbacks. Economic modeling suggests that even a medium-scale eruption could cost the global economy trillions of dollars in recovery. Insurance losses, refugee displacement, and increased demand for clean water and fuel would ripple outward from the United States to affect both industrial and developing nations. Geologists compare Yellowstone to other major volcanic zones, but clarify that it is not part of the Pacific Ring of Fire. Instead, it sits above a stationary hotspot, similar to Hawaii, while the North American plate slowly drifts southwest over it. This movement has left a trail of ancient volcanoes stretching across the Snake River Plain. The hotspot's magma rises from deep in the mantle, gradually fracturing the crust above. In a worst-case eruption, scientists expect strong earthquakes, ground uplift, new cracks, and a huge ash cloud reaching the atmosphere. Fast-moving pyroclastic flows would destroy everything nearby, while ashfall could shut airports, contaminate water, and darken skies over distant cities. However, experts caution against panic. The idea that Yellowstone is overdue for a super eruption is not backed by science. There is no set eruption cycle, and the chance of one happening in the next 1,000 years is less than 1 in 10,000. The 100-foot crack is a warning sign, not a ticking bomb. If one fracture can shift the ground beneath a supervolcano, How close are we to witnessing nature's most powerful reset? What do you think humanity should do next in protecting itself? Drop your thoughts in the comments. If you enjoyed this video, remember to like, share, and subscribe to our channel. Don't forget to check out the next video on your screen. You will enjoy it.